This is the aircraft. To make the aileron tilt at an angle, we are going to create a body transformation. We are going to make a rotation of this control surface at first, apply about an axis, which is this axis, the axis of rotation. Okay, apply. Let's generate. Okay, this is the control surface. If it is tilted, but we are not going to tilt it at 45 degree. We are going to make it at first 5, or at first minus 30, from minus 30 to 30, and we are going to increase 5 by 5. Make a parameterization, make it A for aileron. Okay, now we are going to tilt this body, so rotate this body, apply about an axis, which is this axis. How much? It's going to be at the minus direction. So if this tilted down, this is going to be tilted up. Now this is going to be the same angle, so it's A also. Generate. Okay, now do you see that they both are tilted up? We don't want this to happen, so again go for one of these surfaces and edit, make it tilt in the opposite direction, apply, generate. Okay, now this is the ailerons. This is the maximum angle that the aileron is going to deflect. Okay, now create a boolean, unite all the bodies, apply, generate. Okay, everything is good. But do you see that this is bad for the mesh? So what are we going to do? Don't edit the boolean, make it intersection. Okay, now are we going to preserve the bodies? Yes, we are going to do that, and this make it union of all intersections. Now generate. Look how many bodies now we have. Explode the parts. 1, 2, 3, 4, and 5. Those bodies are going to be suppressed. Okay, Okay, now it works. So we made a boolean. We not just preserved it, but as sliced. Okay, and then this is going to be union of all intersections. Now we have this extra bodies. We are going to suppress them. Here we don't have anything. Okay, then now we are going to unite all the bodies. Make unite. Okay, unite everything. Apply, generate. Okay, now we have one body. Do you see this? It's good. Okay, now let's create the body of influence. Not boolean, but body of influence. Delete this. Yes. Create sketch. Now this is going to be our body of influence. Make a circle, or not circle, whatever you want. For example, like this. I think this is bad. Wait a minute. This is going to be better. Okay, now extrude it and make it not sliced material but frozen. Symmetric, of course. 0 point for me, 7 is good. And generate. Okay, this is our body of influence. Now create the domain. This is good. Now extrude it. And don't use enclosure for the domain. Okay, it's bad for parameterization. Okay, make it 4. Generate. Okay, now this is our domain. Select body. All of them, make them fluid. Okay, make all of them fluid. Okay, now make your name selection. For me, this is going to be the inlet. And generate before. Now this is the outlet. Generate. Okay, let me hide the sketches. Okay, we have 3 bodies. This is the aircraft. Rename it aircraft. And this is the body of influence. And this is domain. Okay, very good. Now we are going to enter another parameterization. Okay, make body transformation and rotation for not this body but the body of influence and the aircraft. So this and this, apply two bodies as you can see. Make a rotation about the Z axis. So here we are going to make it components about the Z axis. This is going to be our angle of attack. At first, let's make it at 24. But this is the angle of attack. This is minus angle of attack, okay? So this is negative angle of attack. To make it positive, change this from 1 to -1. -1. If you want, you can change the coordinate of the rotation axis, okay? Now generate. Okay, it's working. Now we are done here. Let's go to the meshing part. Make edit. Now if you are making for Elevetor, okay, you can make symmetrical analysis, okay, to reduce the time of calculation. Now let's make a mesh. Let's generate to see what's going on. Even if it is bad mesh, it doesn't matter. We are going to just see what's going on. Okay. Now let's change the mesh, reduce the element size from 0.66 to 0.33. Okay. Now we are going to insert sizing. We are going to choose the domain, okay, and then here make it body of influence, and then choose the body inside, okay, the body of influence. Now generate, and let's see. Of course, we are not making a very good mesh. It's just for demonstration. Maybe you can make more on your mesh. Let's make a section here to see inside of the domain. It's looking bad. Not very good. Okay, let's change. We made this body of influence. Okay. Now here, not 0.33, but 0.075. Okay. And generate. Maybe you can add inflation on the walls. Okay, let's add inflation. And here let's make the quality high quality. Okay. sizing. No, let's not change here. And not here. Okay. Now hide the section view. Okay. Insert inflation. Choose this body. And here we are going to choose the faces of the aircraft. Yeah. What do we, oh, wow, we have something wrong. Let's get back. We forgot to extract the aircraft from the domain. Now create boolean here, subtract from the domain. We are going to subtract the aircraft. Okay, we should have only two bodies, the body of influence and the domain. Now generate. Now it's okay. Get out of here, edit. Okay. No, he's telling us that there is body not found. Okay, this is because we extract it from the domain. Inflation. Here choose the aircraft. Now apply. Let's suppress it for a minute. Generate. And let's see how our mesh is looking. Not looking. How our mesh looks like. This is how it's look like. Maybe we can make a mesh with more density. Okay. I think we can do that. So body of influence is going to be 0.04. Don't generate yet, but here unsuppress, edit. Here we are going to choose, as we said, the aircraft surfaces. Hide this surface and hide this surface. And now select box. Okay, hide the body of influence. Now it's going to work, probably. Okay, worked. Now generate. Wait a minute. We are going to increase the layers about the aircraft. Make it 15. Now generate. Okay, this is better. Look, we have now a boundary layer to capture the viscosity. Okay, now we are done with the mesh. It's good enough for me. Now get out of here. Not here. Okay. Update upstream components. Now Fluent is going to import the boundaries from the mesh. Wait for a little bit, and then we are going to open Fluent. Okay, now it's ready. Edit. Make it. It depends on your computer. For me, it's 8. Double precision. Start. Okay, display. Wall domain display. Okay, this is our aircraft because we didn't name it. Fluent automatically named it. Okay, close. Now this is the aircraft. Look, we have Aileron, deflection. Here we have 0. Why is that? Not 0. Actually, it's -30, -30. Okay, now what do we need? We need to start initialization, the initialization of our model. The energy is going to be off because I don't need it. My maximum Mach number is 0.1, so I don't need it actually. The viscous model is also not going to change. It's enough for me. I don't want to change it. Now we have the domain. Okay, we don't need to change the atmospheric pressure, so we are not going to change anything in the domain. Now we are going to change the velocity. Okay, now this is going to change. I'm going to make multiple analysis now for 50 meter per second, and after I finish the 50 meter per second, I'm going to use 40 meter per second, and then 30, and then 20, and then 10. Okay, now it's 50. Okay, apply, close, interior. Okay, the outlet pressure, I'm going to prevent the outlet pressure. I'm going to prevent reverse flow, so nothing get out of the domain and then get back. Okay, apply, close, leave it stationary, apply, close. Okay, now here we are done. Reference values, we are going to compute it from the inlet. This is for the lift coefficient and drag coefficient. Okay, 0.479. this is my aircraft. Okay, if you have another aircraft you can change these values, it depends. Here my aircraft mean aerodynamic code is 0.318. okay, now the method, we are not going to change the method. Okay, we can make here green Gauss cell based. If you want you can leave it as it is, least square cell based. Here new, this is the stuff that we are going to calculate. Okay, for me I'm going to calculate the forces, of course, aerodynamic forces, x and y and z. -1 here, create output parameter, a new one, force, this is the y force, whole domain is 0, -1, and create output parameter, force, z force, here is going to be 0 and here is going to be -1. The forces is going to be on the aircraft, so this is the aircraft but we didn't name it. This is Fluent named it automatically. Okay, now we are going to calculate also the moments, not moment coefficient but the moment. Okay, this is going to be the rolling moment about the x-axis, of course, -1, and create output parameter. Where is the center of the moment? It's going to be the center of the aircraft, the center of gravity, so it's 0. Okay, new one, moment, this is going to be the pitching moment, whole domain, this is going to be -1, create output parameter, new one, moment, yawing moment, which is n on the aircraft, and here is going to be 0 and here is going to be -1, create output parameter. Now we are going to add the lift coefficient to see the lift coefficient. Lift coefficient on the aircraft, here is going to be CL. Okay, the residuals, you can add here 2 zeros. Okay, initialize from the inlet, initialize. Okay, now here we are going to add a plane on the XY plane. On the XY plane, and here we want to see the pressure, the total pressure on the aircraft and on the plane that we created. This is going to be total pressure. This is how we initialized the model. Okay, this is why everything is blue. Now when Fluent calculate the value of the total pressure, the values of total pressure is going to change across the domain. Here a new one. Let's see the velocity on the airplane and on the plane. Here is going to be V. Okay, now let's calculate. Make it 80 is good. Calculate and wait for it to finish. Of course, if you want more accurate, more precise solution, you need to make more iterations. We are going to wait until the solution converge. If you don't have a converged solution, then you need to check your mesh and check your problem, check your boundary conditions. So the yawing moment started to converge. Okay. The rolling moment isn't converged yet. The side force isn't converged yet, but probably it's going to, as we can see here. The oscillations are decreasing. The Z force probably is converging. Okay, the pitching moment is converging. But the rolling moment isn't converged yet. Okay, the calculation is done. Let's see. This is the total pressure around the aircraft. Do you see that? We have here a very high blue area, and here also. But let's see which one is more blue. I don't know. Maybe this is more blue than this, or maybe because of the view. Okay, so we can't really know. Let's make path lines. Start them from the inlet. Here let's skip some of them. Let's say 10. Okay, depends on the velocity or on the pressure. Do you see that? If you want to start them from the aircraft, here make them 50. Do you see that? Might say that there is something wrong, but maybe because of the stalling. Okay, this is 24 degree angle of attack, so maybe the aircraft is going to stall. Do you see that? Do you see that? Maybe we can add the aircraft. Let's add new mesh of the aircraft, save and display, and add this to the active window. Do you see? We have a very huge turbulence. As I said, the results are not going to be precise or accurate. Okay, now we have the X force is converged really. There is no big residuals. There's no big error. Okay, the side force not very converged, but I can accept this error. Okay, maybe you need to make more iterations so it converges, and if it didn't converge, you can change the boundary condition from outlet pressure to the walls. Okay, to make walls instead of outlet pressure. The Z force is not converged very converged, but I can accept this error. The rolling moment also I can accept it. Okay, you might wanna make more iterations to do better analysis. Now we can close this. Okay. Okay, we are done here. Now we are going to go to the parameter set. Here, this is for -30 angle of deflection angle, okay, of the aileron. So now we can make for -25, okay, and then -20, and then -15, and we are going to continue until we reach what? Until we reach 30. I already did this, so I don't need to do it again. I'm going to show you how it is done. Elevetor and Aileron. Okay. So I already did the analysis. Let me show you the data that I collected. This is for the elevator, okay? At first, I collected all the data from, of course, I took angle of attack into consideration. So I made the analysis from -20 to 22, okay, angle of attack. And then for this changing angle of attack, I made a changing angle of deflection for the elevator, okay? And then after that, I made two velocities, two changing velocities, 20 and 50, okay? So the variables are deflection angle of elevator, okay? And before that, we have angle of attack alpha. And after that, we have the velocity, okay? Angle of attack from -20 to 20, for example. And elevator from -3 to 30 to 30. And velocity for only two velocities, 20 and 50. So what we have? We have a matrix by the size of 3 by 3, okay? Not 3 by 3, but it is cubic, okay? Since Ansys is opened now, we can get in Ansys. So this is the data that I already calculated, okay? For 30 elevator deflection angle, we have angle of attack is changing, Okay, and for all of that I am collecting the forces and the moments on the aircraft. And this is it for today.